Hi, this is Real World Audio, and today I'm looking at high efficiency loudspeakers again, comparing high and low or normal efficiency loudspeakers. What is the difference between them? Uh, what is the mechanical difference? So, mechanically, why is a 100 dB driver different from an 80 dB one? And I'm also going to look at what is the workload that they need to provide to reach the same sound pressure level. And I'm going to talk about the consequences of that difference. What sort of demands do they ask from a crossover and from an amplifier? And as you know, this is quite a lot to talk about, and I think maybe this will become a three-part mini series, but yet I think it will be of everyone's benefit to look at these critical differences that we can observe between very high or ultra high efficiency loudspeakers and normal or low efficiency loudspeaker. And for the sake of our examples, I'm going to continue with 102 dB per watt meter efficiency as an example for a ultra high efficient driver or loudspeaker, and 82 dB per watt meter as an example for a low efficiency driver in a low efficiency loudspeaker. So when we look at a driver, I made these drawings yesterday. I hope I can still recall what I wanted to tell with those, but this is how a loudspeaker cone looks like. So this is the basic elements of a driver. So here, this is what we see, the cone itself. And the cone is mounted to a tube, basically, which is behind the cone, and that's called the voice coil former. And the purpose of that is to provide mechanical stability, a unit which can move forward and backward, and as it moves forward, then the cone moves with it, because the cone is attached to the end of the former. And now here we see that this is the voice coil, so basically a coil of wire wound around this former, and that coil of wire is attached to your crossover. Actually, in real life, it is not done like that, but these the voice coil, these are really fine wires. They actually go up to your cone, and they are usually just here, just glued to the cone, to two pieces, and then there's like a thicker wire that runs to a tab on the basket of the cone, and those tabs are attached or soldered to those inner wires in your loudspeaker cabinet that hook it up to the crossover. Just for simplicity's sake, I'm just attaching them right here, because electrically that's what's happening, but taking a much longer path than that. And however, this is really fine and dandy. So between the voice coil former, so like literally sliding in, it's called the pole piece, and that's really a ferrous material. It's just a piece of iron that can be magnetized, and around the voice coil you have the magnet, the loudspeaker magnet, that provides the magnetic field, and this pole piece helps to guide the magnetic lines closer to the voice coil to provide the magnetic field, a permanent magnetic field, because that permanent magnetic field, that's kind of like the stepping ground for the voice coil. So basically, when there's electricity flowing through the voice coil, that creates a magnetic field which will interact with the magnetic field of your permanent magnet, and that will make the whole assembly move back and forth. Now we need stability for this assembly. It cannot just move freely because it would rub, it would fall apart. So we need mechanical elements to hold it in place. And you might think that these mechanical elements are an afterthought, but they are absolutely vital and crucial, and that's why we are calling today's electrodynamic drivers, because this is an electrodynamic driver. It means that electricity is creating the dynamic movement of the cone. We call them the Rice and Kellogg driver, and not call it the Paul Voigt driver, because Rice and Kellogg, they found a way first on how to attach, how to mount this assembly to the basket in a way that it doesn't rub and it's stable. Because Paul Voigt also discovered, also invented the electrodynamic driver in the UK, parallel to Rice and Kellogg in the US, but Rice and Kellogg were the ones who first figured out how to mount them securely to the basket. So then Paul Voigt stopped pursuing it because Rice and Kellogg patented it first. And basically what it needs, what this cone assembly needs to be had in space, is what we see outside on the speakers, which is called the surround. That you see those plastic blips which is going around the cone. I didn't draw it that way, just like lower piece and upper piece, but it really goes around your cone. That's why it's called surround, because it's surrounding the cone. And it's a pliable plastic material, or it can be this harmonica shape, zigzag shape, paper-based material as well. We find usually these two, or in certain cases, like sorry Kintaro, my cat is sleeping over this box, and if you look at this driver, the Diaton P610, in this case they are using neither plastic, neither paper, but they are using leather. They are using goat skin to create the surround. So there's a wide range of material, not wide range, but basically 3 different kind of materials you can use to hold it in place. And all of these materials, they are relatively soft and pliable, and do not restrict the cone movement much if we are talking about fine movements. However, there's the other piece, and this is called the spider, and that's in the back. That's what we normally do not see for most loudspeakers, because you have to take out the driver from the cabinet to see the spider. And basically the spider is attached to the voice coil former, also surrounding it, just like the surround. But the spider is vastly different between a low efficiency loudspeaker and a high efficiency loudspeaker. So for high efficiency loudspeakers, these spiders are much softer, much more pliable. And for lower efficiency drivers, these spiders are hard. And basically, the lower the efficiency of the driver, the harder the spider is. And you can test it by just getting a monster huge woofer which has low efficiency, and you try to press the woofer cone, and it's really hard to move it, to press it in. And that's because it has a hard spider. That's why the movement is hard. And when you have a very high efficiency driver, you try to push the cone in, then you do not feel any resistance at all, because the spider is very soft. So basically, the spider acts as a guide to keep the driver in place. So basically, it will provide it a perfect piston motion. So it does not allow it to slide, of course, because then it would rub against the pole piece, it would rub against the magnet, and that would make a very nasty sound and cause the destruction of the driver eventually. And also, apart from providing mechanical stability, the spider also acts as a handbrake. So basically, the stronger the spider, the tougher the handbrake is. So for a low efficiency driver, it's like having a very strong brake on your driver cone assembly at all times. And I know everyone in the loudspeaker industry are really obsessed about making the cone material as light as possible. But if you make it super duper light, you still have the spider to counteract the movement of the assembly, because even though this thing is light, but when the motor wants to push this assembly forward, yeah, this weight is light here, but there's a strong brake applied to it. So basically, you are losing the benefits of the light cone because there's a very strong spider. And of course, there are still some benefits of the light cone, because if the cone is lighter, then you have less problems with it in theory. So you can have lower resonances, you can reverse the cone movement faster. So basically, if you are pushing the cone forward, it requires energy, and at the end of the signal, when it starts to come forward, then from here to there, you see that change there, then that requires massive amounts of energy to suddenly break the speed. So this is like crashing a vehicle, and then turning it around, like going forward full speed, crash and reverse. And if the cone is lighter, then that crash and reverse process is easier. However, we still have the spider to work against, and that's why we need like 100 watts of power to move the cone forward to create the same sound pressure level as an ultra high efficiency cone would do with only 1 watt of power. This is the key difference, that the handbrake is literally 100 times stronger in a low efficiency driver, and the power of the amp is required to overcome this massive braking effect caused by the spider. So that's one thing. So what are the consequences of that? Of course, when we apply a very strong handbrake, it also means that the low level signals are going to get smeared by that super strong handbrake. Just try thinking about a truck. I have a truck, a Mazda truck, and the trucks have very strong handbrakes. And basically, if I want to start the car and I'm already moving with the car and running, so that simulates like a high SPL scenario for a driver, and then I press on the handbrake, which is a foot pedal in that case, it doesn't have that much of an effect. But if I am parked with this very same truck, so this was the case when I'm going like 60 miles an hour on a main road, and I press on the foot pedal, yeah, I can see it slowing a little bit, but maybe I lost 2 miles per hour or even less than that, not big of a deal. But if I am in the parking lot and I want to start the car, I have the foot pedal on, the car would just like lurch forward a bit, and then come to a dead stop. It won't start, and I need to press on the pedal, accelerate a lot to overcome the force of that handbrake. Now, when you have a personal vehicle, those have much lighter handbrakes, and if you just pull the handbrake in like halfway, that resembles the scenario of an ultra efficient loudspeaker driver, because that's like driving a car with a weak handbrake stuck on. You don't even notice that your handbrake is on because the braking effect is so minimal. Plus, there's one more thing, that high efficiency drivers have stronger motors than low efficiency drivers. So basically, in the case of a super efficient driver, you have a weak handbrake with a turbocharged or a supercharged engine. So you can start the car and even just leaving the parking lot going at very low speeds, you have very nice maneuverability for the car. And now talking about a low efficiency driver, it's like a weaker engine with your super hard brake stuck in. You have trouble going, leaving the parking lot, which is really the analogy for these drivers, low and high efficiency drivers, trying to work at low SPLs. So technically the amplifier is providing both of them with relatively comparable material to give a certain SPL volume, but the low efficiency driver will struggle to create that low SPL sound because there is this massive handbrake which is smearing the image. And I think when you are measuring the SPL and trying to figure out what is the dynamic difference between high efficiency and low efficiency drivers, you can still measure it because it will move back and forth. But the waveform, I am 100% sure that if you want to get a perfect sine wave at, let's say, at 15 dB volume, then with an ultra high efficiency loudspeaker, it will be close to a perfect sine wave. And for a low efficiency driver, it will be something like much more distorted than a pure sine wave, because the spider is acting against the wishes of your amplifier and changing, altering the signal. And now this gives us or gets us to the second part, that there's an interaction going on between the amplifier and the loudspeaker driver. If there was no crossover, then there's a certain phenomenon that can alleviate this problem that I have just described, and that is called high damping factor. So at the next episode, let's have a look at the role of damping factor, and we shall see that it's required in a really specific case. And looking at low efficiency and high efficiency loudspeaker drivers, what are the differences between the damping factor requirements from the amplifiers, and that will make it absolutely clear why tube amplifiers without feedback with low damping factor are a perfect match for ultra high efficiency speakers, and why you need very high damping factors amplifiers to drive low efficiency loudspeakers. So thank you guys for holding on, and cheers. See you at the next video. Please like, subscribe. Bye bye.